Okay, so I've started the recording. Now, as I was saying, if you are doing a proof in matrix, right, you don't have to use numbers. You don't have to use actual entries. So you can't define the matrix A as, let's say, 1, 4, 1, 1. You can't even say let A be equal to this. No, let A be because it doesn't work that way. So the best option you can use is using let's say A, B, C, D, or you can also use A 1, 1, A 1, 2, A 2, 1, and A 2, 2. So that for every entry, the first I represents the row number and the J represents the column on which it is found. We went through this intro yesterday, right? So as I was saying, if you are doing a proof, please don't use entries, else you won't be marked, right? Now, a skew symmetric matrix is a matrix that when you find the transpose, right, is equal to negative of the original matrix. So let's have a recap on what we did yesterday. We said if you have a matrix A being equal to A, B, C, and D, the transpose of A, right? The transpose of A, AT is equal to AC, B, and D. This is what we have. Where the column becomes the row and the row becomes the column, and vice versa. Right? This is basically what we have. Now, when a matrix and its transpose are equal, then we say the matrix is what? Symmetric. Pardon me for my spelling. And if the matrix A is equal to negative its transpose, then it's skew symmetric. And this is the case that we are using over here, right? We are being asked that let A be a skew symmetric matrix, find the trace of A. Now, this is the most popular way you can represent a matrix as a skew symmetric matrix. Okay, so we can use this one. So you can write this down. Okay, if we are using a 3 by 3 matrix, or should we use 2 by 2? Let's see if it was defined. Okay, so let's use the 2 by 2 matrix first. So a 3 by 3 first, then we see how we can get a 2 by 2 matrix from it. So let's have A, B, C. For a skew symmetric matrix, you basically have the negation. So this, let me write it down so that you can copy it later, right? This is how to represent a matrix as skew symmetric, right? Now, the reason why this is following, you can't just represent it by any of the terms is that when you find a transpose, when you find A transpose, you should get negative, how should I put this? So when you find A transpose, you should get negative A. Yes, basically. That's what makes it a skew symmetric matrix. So with this, if you find the A transpose, this section of the class is a bit boring, but please stay with me, okay? Matrix is some way. Okay, if you don't get something, kindly stop me before I proceed. So with this, if we find a transpose, we get A, negative E, and negative D. For the second column, we get E, B, negative F. And finally, we get D, F, and C. Now we can see that the transpose A transpose is actually equal to negative A, right? So you can write this down and use it whenever you are doing such a proof. So let's see if you can get an equation, something similar for a 2 by 2 matrix. So let's see A and B negative C, and C. So let's see if this works. So we have A transpose, and we have A negative C, and we have CB. Of course. So this is how you can go about it for a skew symmetric matrix. Now the question states that find the trace of A. Find the trace of A. Now this one, let's really understand this carefully. So a trace of a matrix is the sum of the entries on the major diagonal. We saw in yesterday's class that the major diagonal is a diagonal which includes the first entry A11 to the last entry Aij. So the major diagonal will include everything which is located on this major axis. Of course, this diagonal is known as the minor diagonal. So the one in red is the major diagonal, and of course, the one in yellow is the minor diagonal, right? So we have to show that for this 2 by 2 matrix, A plus B is equal to 0. Or for the case of a 3 by 3 matrix, A plus B plus C is equal to 0. Now, think about this, right? Think about this. Is it possible, right, that we can add numbers and give us 0, and they'll give us 0 in any condition? Of course, if we have something like this, then A should be negative and B should be positive A. They should be similar but different signs. With this one also, we are adding 3 numbers. So one should be positive, one should be negative, and one should be 0. Now, the only condition, the only way that a matrix um, can be skew symmetric, right, is if hey, what am I saying? Is if its major diagonal, all the entries are equal to 0. And you can look at the examples that we have, right? So how do you solve this? You conclude that for the sum so you conclude that the sum of the entries of a skew symmetric matrix is always 0, right? Because then you can make an right, you just write something, you get a mark, right? They are just testing whether you know that the sum of a skew symmetric matrix is always 0, right? You have to write these equations down and you conclude. There's no direct solution for this, but that's how we go about it. Okay. Now let's go with the third one. Let A be an n by n scalar matrix, and let A be equal to Ki. Find the trace of A. I plan on doing this in 10 minutes, but it's like time is really going fast. Wow. So n is a scalar matrix. When you are given a question like this, don't bother using a 3 by 3 matrix. As much as possible, use just a 2 by 2 matrix, right? So A is a 2 by 2 matrix. Let's use a 2 by 2 matrix. And the reason why I'm using a 2 by 2 matrix is because it has been stated in the question that A is a scalar matrix. Oh, sorry. So if A is a scalar matrix, then let's multiply this identity by a constant, let's say K, right? Because a scalar matrix is an identity matrix which has been multiplied by a constant, right? That's what a scalar matrix is. So find the trace of A, right? Find the trace of A. Now, what's the trace of A? This is the size of the matrix. And we can see that for a 2 by 2 matrix, the trace of A is what? K plus K. So we get 2K. For a 3 by 3 matrix, we get something like K, 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 get 0, 0, 0, 0, 0, 0. So we get K plus K plus K again, and we get 3K. So there's a trend over here. So the trace of A is equal to the N, which represents what? the size of the scalar matrix times the scalar constant K, right? That is how we get the size of a matrix. Sorry, that's how we find a trace of this matrix, right? Now let's solve the final one. Let I be an n by n identity matrix. Okay, so if you are if you are in our calculus class, right, the one we had just before this, that one is much faster, and because that one is just for 4 days, but we have about 8 or 7 days to prepare. So I'm taking my time so that we really go through everything, right? Yes. So let n be an n by n matrix. Find the trace of I. N by n, and again an identity matrix. So let's see. Let's use a 2 by 2 identity matrix. 1 1 0 0. And we are being asked to find the trace of I. Right? The trace of I. And once again, the trace of I is equal to n times I. N times 1. Right? Because in this identity matrix case, your K is now 1. So this formula still holds. But for the case of the identity matrix, your K is 1, so it's still n, which is the constant, times n, which is the size of a matrix, right? Times your constant, which in this case is I. Remember that identity matrix, scalar matrix, they all fall under square matrix, right? Matrix that have the same number of columns and also same number of rows. So you don't have to worry about uneven length or something, right? It works for all. And this is basically what we have to do for today. I'll be posting um the questions for tomorrow also in the group, right? Now those ones will be exercises, not from the slides. These ones are slides, but the one I'll be posting next will be a bit more advanced. All right. So now let's move on. Let's move on. Today we'll be doing a lot. So this how it's going to be. We are going to be treating the three models of 1 to 6. For the first 3 days, we'll be doing matrix. The second 3 days that we have, we'll be doing complex numbers. Then the final one, we do the third model. Then we are done. Right. So let's start something new. So the the first of them is determinant, right? Determinant. Please, if I'm moving fast, let me know. Okay. And again, we'll be using a 2 by 2 matrix. So let's use a matrix A, which is equal to A, B, C, and D. So the determinant of A, which is represented by det A, is basically equal to A times D minus B times C. Right? This is a case for a determinant when you have a 2 by 2 matrix. So if you have A being equal to 5, negative 4, let's say 6, negative 5, the determinant of A is basically equal to 5 times negative 5 minus negative 4 times 6. The reason why I brought this question specifically is because of this sign. A lot of people solve determinants, and like the questions are tricky. They know that you are expecting a negative here, so they bring a value that already involves a negative. So if you're not careful, you are going to miss this negative sign and take this negative sign to be the negative that should already, like, how should I put this? take away this negative sign, use this negative sign instead. So you have to be careful, right? Always bring your negative sign before you do your product. So this gives us negative 25 plus 24, and finally we get negative 1 for the determinant. Now, the second thing is that the determinant for an identity matrix, as we saw, is always 0, right? Because basically you are multiplying this minus a product of 0. So we get the determinant of I, an identity matrix, is equal to 1, right? Let's look at minus and cofactors. As I said, there's a way to do all of these with the calculator, right? So you have to know how to do each and every single one of this with the calculator. Minus, cofactors, adjoints, even trace, the one we just did, can be solved with the calculator. Inverses can be solved with the calculator. So almost everything in 126 model 1 can be done with the calculator, right? But still, we have to know how we go about them. Then later we learn the tricks to solve with the calculator. Then we just solve to an answer when we are given a question. So let's look at minus and cofactors. So let's have an n by n matrix. Let A be an n by n matrix, or let A be a square matrix. So let me use a 2 by 2 3 by 3 matrix for this case. A1 2, A1 3. So A2 1, A2 2, A2 3, and finally we have A3 3. So A3 1, A3 2, and A3 3. Now, this is the formula to find the cofactor of a matrix, and it's a bit some way, but Aij, let me use my red pen for this. Aij is equal to negative 1 to the power I plus j times the determinant of Mij. Now, let's break down this formula, okay? This part here, you don't have to choose, you don't have to really understand it. It's actually quite simple. The I is the number of rows that we have, the J is the number of columns that we have. So every entry, you input in the number of column and the number of rows to determine the sign of your entry. So when you do that, you are going to get a table that looks like this: plus, minus, plus, minus, plus, minus, and plus, minus, plus. Basically, this is what your matrix would look like, basically, right? That's for this part. Okay. Now, this thing here, let me add this to it before I forget. Add joint. So before this in what a determinant is, this formula over here is the formula of an adjoint, right? And I know I'm writing so much on the board, but we'll break it down when we solve one example. Okay, so let's take one example and let's find the matrix of minus, the matrix of cofactors, and finally the adjoint. Let me see if I can get an example. Let's see. Okay, so let me use this example. Let's see. Let me see for this one instead. Yes, so this makes more sense. So let's take a look at what's the minus and what the cofactors are first. All right, so we have a 3 by 3 matrix. The matrix of um the matrix of minus is the determinant of each entry. So I know it's some way, but let's break this down. So the minor of A11, right? What you have to do is that you have to cross this one, you have to cross this one, then you get this matrix. So the minor of A11 is basically equal to the determinant of A22, A23, A32, and finally A33. Then you continue, you find the minor of A12. So A12 will also be equal to the determinant of A21, A31, A23, A33, and you continue A13. This will be my final one. Or this, please, it should be a straight line, not a bracket, because using a bracket means that you're actually doing it's actually a matrix, right? These two straight lines mean it's a determinant you are finding. So A13 will also give us this internal part, which is A21, A22, A31, and A32. And you continue and do this for each and every single one of this. I know it's work, yes, it is, right? So when you finish doing this, you have a matrix of minus. Now, this is a formula for the matrix of cofactors. Once you find the determinant of each entry using the matrix of minus, and you apply this formula, basically, wherever you see an entry, you just multiply it by plus, minus, plus, minus, minus, like in that order. When you do that finish, you get a matrix of cofactors. Let me come with this again. The matrix of minus is the matrix we get by finding the determinant of each of the entries by doing the crossing out method and finding the internal determinant as we've done here so far. Now, when you are done, you can multiply each entry by its corresponding power, right? So once you do that, you no longer get a minor, but you get a matrix of cofactors. Now, once you get a matrix of cofactors, how do you get an adjoint? Yeah, we'll be taking one example. Okay, so if you don't get it fully, um, it's not a big deal, but we'll be taking one example very soon. So just a minute, just a minute. Before we look at the adjoints, let's take an example first. I'm looking for an example that will not take our time. Because this, just a minute. Okay, so let's use this example. So let's have the matrix A being equal to 1 to negative 1, 1 for negative 2, 2, 3, and 1. Right? So the minor, the first entry will be minor M11. The second one will be minor M12, M13 in that order, M21, M22, M23, M31, M32, M33. Yes. So now the minor M11, right? The minor M11, how can we get it? We get it by crossing out this section. When you cross out this section, you are left with this internal matrix, right? So this internal matrix is basically equal to is basically 4, -2, 3, 1. So we have 4 minus minus. We have 4 minus -6, and this is equal to 10. Again, they brought this same thing again, right? So this is one very similar, like one very common something that you should take note of. And a lot of people make these mistakes by not bringing the negative when they make the multiplication, right? So A12, which is now we cross this, we get a matrix 1, -2, 2, and 1. Okay, so this gives us 1 minus 4, and this is equal to 5. A13 is equal to this will be my final one. So negative, we get 1, 4, 2, 3. We get 3, -8. This gives us -5. So let me try and do this quickly so that we can move on a bit fast. So we have A being equal to, we've already done 10, we've done 5, we've done -5. This gives us 5, -1. Okay. So this basically, let me cross check this one last time. Okay. So I think we are on track. Yes. So this basically, right, is your matrix of minus. This is your matrix of minus. And how did we get this? We got this by finding the determinant by crossing out the entry that we are finding the minor of its rows and like columns. And the inner matrix left, we just find the determinant of it. And that gives us the determinant of that matrix, which is the minor of that particular entry, right? That's what we've done throughout, and we've been able to get this matrix, right? Now, the second thing is to find a matrix of cofactors, and we are going to use the formula what? Plus minus plus minus plus minus plus minus plus, right? So once we are able to do this, what do we get? We get 10, -5, -5, -5, 3, -1. We get -5, 1, and as well as 2. This is the matrix of cofactors. Now, let's look at what the adjoint is.
Hello, Ben.
Yeah, hello.
I don't get the difference between the minors and the cofactors. How is
Okay.
yeah,
Okay. So let's go over this again, right? So when you when you do these computations, right? But do you get how we did these computations? How we went through these ones? How we crossed out the values to get the inner determinants for each session?
Yes, yes, I understand
Okay.
how we got the
Yes.
minus.
So okay. So when you get your minus, right? When you get your minus, this is the formula for the cofactors. This is the formula we are using for the cofactors. And this this thing here is basically the formula for, like, how should I put this? The entry for a minor. So we are saying that, okay, find a matrix of minus. So let's say you have the matrix of minus being equal to AI, A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, when you have your minus, to turn your minor into the cofactor, you refer to this table, this matrix, right? This matrix is basically this thing we are having over here. So let's use this formula. The column of the row number is equal to 1. The column is equal to 1. So this will be equal to negative 1, 1 plus 1. The second one also will be equal to negative 1, 1 plus 2. Again, negative 1, 2, 1 plus 3. And we go in that order: negative 1, 2 plus 1, negative 1, 2 plus 2, negative 1, 2 plus 3. Now, when you do all this, you get the minor to be equal to I negative A12, A13, negative A21, A22, because 2 plus 2 is positive, so the negative goes away. 2 plus 3 is odd, right? So negative 1 to the power an odd number is equal to an odd number as well, right? So we get A23, then we continue in that order, right? So this also gives us what? 3 plus 2 to the power negative 1 to the power 3 plus 2, which gives us 1, negative 3, 2. So instead of, so when once you do this, this is what we mean by this, not the, I know. This is what we call the minus. Oh, okay. So the matrix of the determinant something, right, is what we call the minus. Now, once you add the negative and the positive something to it, that's where you get the cofactors. So this one is not part for the minus, this one is not part. We don't do this computation. We just find a determinant and put it in that way. But once you want to find a cofactor, you can use this formula. This formula is the same as this matrix here that we are having, right? You just multiply it with positive and positive. So we can see that this is positive, this is negated, this is positive, and in the next row we have negative, positive, negative, or this should be negative, and again positive, negative, positive, right? Because we are following this trend. Instead of computing it every time, you can just follow this matrix and get your cofactors from them. Please, should I go over one more time, or is it okay?
Hello, Ben.
Yeah, hello.
Initially, you mentioned adjoints, right?
Yes.
And I think adjoints, you were using the same formula, or adjoints uses a different one.
Yeah, adjoint is a bit different one. Sorry if I mentioned the adjoint. Maybe I mixed it with the cofactors, right? But the adjoint is a bit
Okay.
different from the cofactors. So this is how it works. You find the minor of a matrix by using the determinant something, right? Then you do your plus minus something to find the cofactors. Now, once you have the cofactors, this is the formula for the adjoint. So with the adjoint, the adjoint is basically 1 on the determinant of the matrix. Then you multiply it by the matrix. So for the adjoint, you find the determinant of the entire matrix, right? And you multiply each entry by 1 on the determinant of the matrix. So let's pick this example, right? Let's pick this example and let's use this example for it. Just a minute, please. Just a minute. Um, Sorry. I'm mixing something here. Let me confirm it. Just a minute, please. Let me go to my slides. Um, I I think I'm missing two things here. Let me check this. Let me check this real quick. Transpose. I'm looking for a particular slide to find. Just a minute. I think when we take an example, this would make so much sense. So let's pick an example, right? Let's pick an example. Let's wait on the adjoint, right? This can wait because um it's getting a bit messy and I'm getting confused myself. But let's pick this example. I'll not be using a 3 by 3 matrix, but rather a 2 by 2 matrix. So let's have E to be equal to 5, -4. Let's say 6 and -5, right? So with this, we are going to find a matrix of minus. We are going to find the cofactors, and then we are going to find its determinant. We are going to find the adjoint as well, right? Now, the first thing that we find is the matrix of minus. So this is a 2 by 2 matrix. So when you cross out this and you cross out this, you are left with 5, -5, right? So the determinant of just one entry is still that entry. So the matrix of minus, let's say is -5 for the first entry, right? So for -4, we cross out this, we cross out that, you are left with 6. For 6, we cross out its row, its column, we are left with -4. For -5, we cross out its row, its column, its row, we are left with 5. And this is our matrix of minus, right? This is our matrix of minus. When we do this, we are done with the matrix of minus. Now, again, to find the cofactors, all we have to do is to say plus minus and plus. It goes in that order, right? So for the matrix of cofactors, we get negative 5 times negative and positive, we still get a negative, right? Sorry, let me not even use the example. Um, you are having a negative number, right? And you are just let me see. I don't say multiplication because multiplication, yeah, I think the word multiplication can work. Yes. So you are basically multiplying, right? So let's assume there is one here, there's one here, there's one here, basically, right? So negative 5 times 1 is basically negative 5. Negative 1 times 6 is basically negative 6. Negative 1 times negative 4 is 4. And of course, we have 5 over here. So all we did was that this was the value we got for our minus. This, this, and this. But once we do this plus minus minus plus something, which in this case for 2 by 2 matrix, then we get our matrix of cofactors. Okay. Now the third thing we have to find is the determinant. So for a 2 by 2 matrix, we just negative 5 times 5, and we have negative 4 times negative 6, and we get negative 25 plus 24, we get negative 1. The second thing we have to find is the matrix of adjoint. Okay. So the adjoint, we are going to use the matrix of cofactors. Exactly. So for the adjoint, right? So for the adjoint, what we do is that we find the transpose of the matrix of cofactors. So initially, I was given a formula for the matrix of adjoint, but that's not the matrix of the adjoint. That's rather for inverse. We've not gotten there yet. And yes, so that's not the formula for the adjoint. Thank you for calling me out. The matrix of adjoint, we basically find a transpose of the matrix of cofactors, right? So to find the adjoint, we find the transpose of this matrix, and we get what? Negative 5 and 4 is vertical, so it becomes horizontal. Negative 6 and 5 is vertical, it now becomes horizontal. Once we do this, we have our matrix of adjoints. Let me just represent this by AG, right? Now, all these three things or four things that we are finding, you can be asked to find any of them. You can have a question that is only asking you to find a matrix of minus, cofactors, a determinant, and adjoint, right? But all these things help us to come um, to find an inverse, right? All these things help us to find an inverse. So this is the formula for an inverse. There is a proof for this, but you will not be examined on the proof because it's quite long. So I'll not be taking you through the proof, but you can check it out later. And believe me, you will not be examined on the proof because it's basically not in the slides. Like it's not covered in the slides anyway. So this is just one of several formulas that we would be looking um, for the inverse, right? So the inverse of a matrix is 1 on the determinants times your matrix of adjoint. So in this case, we've been able to find the matrix of adjoint and also our determinant. Our determinant was what? Negative 1. So to find the inverse, we get A inverse is equal to 1 on the determinant. The determinant, we got negative 1 for it. And the adjoint is negative 5, 4, negative 6, 5. So we have negative 1, being multiplied by -5, 4, -6, and 5. And this leaves us with 5, -5 times -1, 4 times -1, -6 times -1, and again 5 times -1. So we get 5, -4, 6, and -5 as our inverse. I know this is a bit messy, but let's go over this one more time. We started by finding the matrix of minus, and we said to find a matrix of minus, you do this cross something, right? So you cross the row and the column on which a matrix is found, and take your inner matrix and find a determinant of it. That was the case of the 3 by 3 matrix, where we got these minor formulas in this form. For the 2 by 2 matrix, when you cross out, you only get one entry. So you write your entry as it is because you can't find a determinant of just one entry. Once you populate your table of minus, you use the formula -1, sorry, -1 to the power I plus j. Or you can just use the table positive, negative, negative, positive for the 2 by 2 matrix, or positive, negative, positive, negative, positive, negative, in that order. Once you do this, we get the matrix of cofactors. Of course, we know how to find a determinant of a 2 by 2 matrix. We'll get to finding the determinant of a 3 by 2 matrix, 3 by 3 matrix next. But this is basically the formula for finding the determinant of a 2 by 2 matrix. Now, you found the minor by using the determinant of each entry. You find the cofactor by doing the plus minus plus something. We know how to find the determinants. Now the adjoint is the transpose of the matrix of the cofactors. So the adjoint is equal to the cofactor that has been transposed. Now, once you have your adjoint and you have your determinant, you can find your inverse, because the inverse of A is equal to the one on the determinant of A times the adjoint of A. So once you do this, you have the inverse of A. That gives you your inverse of A formula. And please, do we get this, or do we need one more example? Is any part not clear? I want to hear from everyone. Is it clear? Because this is very important before we move on to, okay, a thumbs up from Godfred. Hello, Judy. Hello, Kojo, Annabelle. Okay, so let's move on. So let's see how to find the determinant of a 3 by 3 matrix. The determinant of a 3 by 3 matrix. And I think with this one, it's best we take an example. Right. So let's go through the two ways we can find the determinant of a matrix. How should I? Okay, let's just use the first one. The second one, I think it's not in the slide, so let's use just the one that we know. So this is the matrix that we are having. We have the matrix A being equal to 1, 2, -1, 1, 4, -2, 2, 2, 1. To find the determinant of A, which is date A, right? It's basically A 1, 1, the minor of A11 minus A12 the minor of A12 plus A13 the minor of A13. Now, basically, to find the determinant, you can use any of the rows that we are having, right? But how should I say this? You have to follow the minor to cofactor convention, right? So this is still positive, negative, positive, negative, positive, negative, positive, negative, and positive. So because I was finding the determinant using the first row, is it a row? Using the first row, the -2 becomes like a subtraction, right? And of course, this becomes positive. The first one is already positive. If I'm finding the determinant of A using the second row, I'm going to get negative A21, the minor of A21 plus A22, the minor of A22, and minus A23, the minor of A23. And when you do each of these, you get the same answer for all of them. These should give you the same answer, no matter the row you are finding the determinant on. Right. So again, let's use this example. So the determinant of A is equal to A11. A11 is 1. Let's find the determinant of the matrix of minus of A. So the matrix of minus of A is of A11 is basically 4, -2. We have 2, 1 minus 2, 1, 2, -2, 1. 1, 2, -2, 1. And because -1 is already negative, this positive goes to negative, right? Because you have plus -1. So we just use the negative directly. -1. Then we have the matrix of minus, which is this section 1, 4, 2, 2. Now we have to find the determinants of each of these three something. So 1 times 4 plus 4, -2 multiplying 1 plus 4, -1 multiplying 2 minus 8. And this gives us 8 minus 10 minus 14 minus 10, which gives us 4 for our determinant of A. So let's have a recap of finding the determinants of a 3 by 3 matrix. We said that we can use any of these three rows. You can use the first row, second row, or the third row, right? But you have to take note of the sign. When you're using the first row, the first is positive, negative, and positive in that order. And of course, the second row takes negative first and goes to positive at the end. You find the determinant of your matrix of minus and you end up with this. So this is how we find the determinant of a 3 by 3 matrix. Now, the next thing we'll be looking at is linear systems, right? So First of all, we have to understand that every matrix is a number of equations that have been written in a glorified manner. So if you have a matrix such as like 2, 4, 5, 6, 7, 8, 1, 1, 0, this is basically an equation, right? Three equations that you are having that have been written in the form of a matrix. So we can use matrix to solve linear equations. So if you have something like ax plus by is equal to x, so let's say this is your first equation. You have cx plus dy to be equal to t, and this is your second equation. So this is your first, this is your second. So once you have something like this, you have two separate equations. You can solve this or represent this using a matrix. So how will we solve this using the normal um, equations way, right? So you want to find x or find y. So let's multiply the, so let's try and get rid of the x so that we basically have one expression in terms of y, then we find our y, and after we find our x, just as we do in normal equations. If you have 3x plus 4y is equal to 1 and 2x plus 2y is equal to 2, basically multiply the top, the first equation by 2 and multiply the second equation by 3. So by doing so, you get something like 6x plus 8y is equal to 2. 6x plus 4y is equal to 6, right? So having x of similar terms, you can either add or subtract to get rid of your x. You have just one term here, so you can basically find your y easily. That's something similar we are coming to do. You are multiplying the first one by c and multiplying the second one by also a. So this leaves us with acx plus byc. Let's not mix this. So cax plus cbycx. Again, we have acx plus ady is equal to 80. So let's find the subtraction of these two. This and this goes away. We are left with cby minus a dy. This is equal to cs minus at. Let's factor out our y. So we get cb minus ad. This is equal to cx minus at. So this is what we get when we solve for our y. Right now, what deductions can we make from this that we've done? Right, look at this carefully. Okay, this is actually the same form as the determinant that we know. So y is basically the solution to y is basically the determinant right? It's basically the determinant of what cx at cbad. So this becomes the determinant, this becomes the answer to our y, right? So let's try and make the relation. Where is our y? Where is our y? Okay, so let's take one example, okay, and try and use this same principle, and let's see how this works out. So let's use the example 5x minus 4y is equal to 2. We have 6x minus 5y is equal to 1. So now, the reason why I try to do this is because you can be given these two equations, right? And to prove that the answer for y is equal to this. So you have to go through these things to arrive at this. This is actually a question that I've actually seen before, right? So knowing how to use terms that are non-numbers is actually very good, right? So it's a bit boring, but like that's what we have been examining on. So this is an example that we have. Okay. So using the same um using the same form, it's basically let's see. We basically multiply the first equation by 6, the second equation by 5, which we get 30x minus 24y is equal to 12. 30x minus 25y is equal to 5, right? We find the subtraction, we get y is equal to 7. Now let's try and use this formula, something that we've seen. Okay, so this is the original um question that we have. Okay, and we've seen that. Let's try and write this again and make the relation from it. Ax plus by is equal to x, and cx plus dy is equal to t. Now let's start with the denominator. Please watch this carefully, right? Our denominator is basically AD. Let me check this just a minute. Cx CD. Okay, just a minute. Let me try and rewrite this in a different form. So it's the same thing that we are doing, but I'm multiplying both the numerator and denominator by negative, right? So I'm multiplying both of them by negative so that I get a standard form that I want to use to explain, because the form I have is correct, but it won't make what I want to explain clear. So with this, we get AT minus CX all on AD minus CB. Okay. Now this makes it more clearer. Now take a look at this carefully, right? So this is basically equal to, let me use the red pen. This is basically equal to the determinant of AX CT on ABCD. Now we can see that this determinant, this numerator determinant, is the determinant of this part of the equation. Please pay particular attention to this part. This determinant here is equal to the determinant of this part of the equation. Now the determinant at the top side, right, is equal to, we had this side being maintained, but every side at the y section is replaced with our constant at the far right. Let me go over this again. We got the formula for y, right? Using the normal way we solve it, using elimination, right? And we got this for our y. Now we notice that the numerator and the denominator of y follows the same formula that we have for the determinant. Now, when we extracted the determinant formula for the y expressions that we have, the denominator of the y is equal to the determinant of the inner part of our equation, this section. And we are having the numerator to be equal to, we have the ACB maintained, but every part on the y column has been replaced by S and T. Remember, this is our value for y. Now, this is basically the proof for the Cramer's rule, right? So let me write the Cramer's rule, and hopefully this looks more nice. So x is equal to, let's say, so we have these three matrices. Let's see, the matrix A is equal to A11, A12, A13, A1, A21, A22, A23. Finally, we have A31, A32, and A33. This is what we have, right? Now, with the Cramer's rule is saying that, okay, the value for x, remember that this column is for x, this column is for y, and this column is for z. The value of x is equal to what? We replace every entry in the x column with our c. So our c is what? Let's say c1, c2, and c3. So the x column now becomes c1, c2, c3, a12, a22, a32. You have a13, a23, a33. On what? Remember that we also have the determinants of the original matrix that we have over here. So we also get this on the determinant of A11, A12, A13, A21, A22, A23, A31, A32, and finally A33. So all this we've done is just the formula for finding X. To find Y, we use the formula what? A11, A12, sorry, let me use the now we replace all the entries in the Y section with what? With this C1, C2, C3, and again this on the original determinant matrix, which is what? A11, and it goes in that order, right? So this proof that we have here, this is the Cramer's proof. By using the normal elimination method, getting a determinant expression, which you can link it up with the determinant formula and establishing these relations. This is basically what the proof for the Cramer's rule is, right? So just as we did, if you do this and it doesn't look nice or it doesn't make sense, you can multiply it by negative both numerator and denominator, and hopefully you get something that makes more sense, just as we did, right? Is there anything confusing? Should I go over this one more time, or it's okay? Um, Hello, do we get it?
Please, can you go over?
Okay, let me go over this again. So this was the equation we began with, right? We began with this equation, and we said that this equation follows the same way that the normal simultaneous equations follow. So when you have this simultaneous equation, you try to have one thing, maybe X or Y, having the same entry. So we want to make this one 6x and also this one 6x. So that we can just eliminate the X, just as we did over here. Now, once we eliminated the X, we just subtracted and got the value for our Y. That's the same application that we are also doing in this case, where we have Cx and Ax. So we multiply the Cx by A. We are trying to get rid of the this entry, right? The X in both the first and second equation. We multiplied the first equation by C and the second one by A. So this was what we had. We subtracted and cancelled out and got our value for Y. So we made Y the subject in this case and factorized and got this expression for Y. Now we multiplied both the numerator and denominator by -1 and got this expression over here. And this expression over here is basically the determinant of a matrix. Now we extracted the matrix from this determinant formula and got this. Because if you are finding the determinant of this, is what? AT minus ST on AB minus BC. This is what we have. So from this, Cramer said that, okay, to find a determinant, all we have to do is that you have to find a determinant of the original matrix and divide it. So it's basically the formula to solve for X, right? You are basically doing the X on D, where the X is the determinant of your matrix, but the entries of the X has been replaced with your C at the far right side. right? So y is also equal to dy on d, and z is also equal to dz on d. Basically, this is what we have, right? So the d we are saying here is the determinant of the inner matrix, like A of just the E's. But the X, you replace all the entries in a particular column with that of your C's. Please hope this is clearer. Hello.
Yes.
Okay. So let's proceed. Let's proceed. Now we've looked at one way of finding of solving a linear solution, right? And this is the way of using the Cramer's rule. Okay. Now there are two more ways to solve a linear solution, right? We'll be looking at the Gaussian elimination, and also using the inverse. Now, first of all, let's look at how to solve a linear solution using the inverse. So let's say we have ax being equal to b. Once we have this, right, we can multiply both sides of the equation by the inverse of a. And this gives us A inverse AX is equal to A inverse B. So this gives us the identity matrix I X, and this is equal to A inverse B. So X is basically equal to A inverse B. Now let's take one example. We have the matrix 5x minus 4y is equal to 2. We also have 6 is equal to negative 5y, and this is equal to 1. So with this, we can see that our matrix is 5, negative 4, 6, oh no, 6, negative 5, xy, this is equal to 2 and 1. So we said that to find an inverse, we first have to find the minus cofactors. We find the adjoint. Now from the adjoint, then we can find the inverse of the matrix. Right? So that's what we are going to do right now. So we are finding the minus of this matrix. We cross this, we get negative 5. We cross this. Sorry, we cross this. We get 6. For 6, we cross this, we get negative 4. For negative 5, we get 5. This is a matrix of minus. This is equal to M. To find the matrix of cofactors, we use the plus minus plus. So negative 5, 6, negative 4, 5. So basically plus minus minus plus. So the cofactors is equal to we have negative 5, negative 6, 4, and 5. And this is equal to the matrix of cofactors. We now have to find the adjoint. We know that the adjoint is equal to the transpose of the matrix. So the transpose of this matrix gives us what -5, 4, -6, and 5. This becomes our adjoint. Now the next thing we have to do is to find our determinant, right? So our determinant is, of course, -5 times 5 minus, let's group like terms, 4 times 6 is -25 minus. So our determinant is equal to -1, right? So the inverse of the matrix, so the A inverse that we are looking at here is equal to, of course, 1 on the determinant of A multiplying the adjoint of A. We have the determinant to be equal to -1, 1 on -1 times the adjoint, which is what? -5, 4, -6, and 5. So A inverse is equal to 5, -4, 6, -5, and this becomes our inverse. So all we've done is just finding the inverse. And why did we find the inverse? We found the inverse because of this equation we want to solve, right? So our inverse is -5, 5, -4, 6, 5. We have 5, -4, 6, -5, 6, -5. This is our inverse. Now, what is our B? Our B is basically 2 and 1, right? So we have 2 and 1. So we can multiply the row to the column. So 5 times 2, again, because we have a 2 by 2 matrix, multiplying a 2 by 1 matrix, our resulting matrix will give us a 2 by 1 matrix. We saw this yesterday, because the column of the first matrix should be equal to the row of the second matrix, and the resulting matrix would be the row of the first and the column of the second, right? So 5 by 2 so 5 by 2, -4 times 1, 6 times 2, which is 12, minus 5 times 1. So this results in 10 minus 4, which is 6, 12 minus 5, which is 7. So with this, we can tell that the answer for our matrix, right? Where's our question? So from this, x is equal to 6 and y is equal to 7. I think we solved this matrix somewhere. Yes. So we got y to be equal to 7 when we use the normal elimination something, right? So we've just used the inverse method to solve for our matrix, and by doing so, Again, we got y to be 7 and x to be 6. Please, do we get what we just did? How to solve a matrix using the Cramer, which we went through some time ago, and now we've seen that we can also solve a matrix using the inverse. Because we have ax to be equal to b, we can take the inverse on both sides of the equation. We have a inverse, a matrix and its inverse gives an identity matrix. So we have x being equal to the inverse of the matrix times its constant, right? So all we have to do is to find the inverse. That was the heavy part. Then we just had to multiply by the c's that we had. Any questions? Hello, any questions? Should I go over or am I confusing you? I know it's messy, but hello.
Go over again, please.
All right, let me go over this again. So let me use my yellow pen. So this is the equation that we have, right? And we basically want to find x, and x is not just any x, but x is actually a matrix, right? So x is basically x, y, and z. But in this 2 by 2 matrix case, x is just x and y. Now we can multiply both sides of the equation by the inverse of a. When we multiply by the inverse of a, we get an identity matrix x, and that is equal to the inverse of a times b. So we get x being equal to the inverse of a, right, times b. This is the key part. This part is the key part. Once you get this, you are good to go, right? You multiply by the inverse, we get the expression x is equal to the inverse times b. So all we have to do now is to find the inverse of a and multiply by b. So we started by finding the minus. We found the cofactors, we found the adjoint, and we find the inverse. So we know how to find the minus and cofactors and adjoint. And we said that to find the inverse also, all we have to do is to take the adjoint, find the determinant of the matrix, find 1 on the determinant, and multiply each entry of the adjoint by 1 on the determinant that we are having. And when we do this, we have our inverse. Now we found our inverse. This is the formula that we are using. So we slotted back our inverse to the equation and multiplied it with the value c that we were having. The value c that we had was what? We had, these are the value c's that we are multiplying with. Hope is clear. I'm recording the session, so we can go over again if it's not clear, or I'll be sending more materials and more practice questions so that we practice more. Okay, so let's look at something. We've done the solve systems of two linear equations. Yeah, so this is using the Cramer's rule, as we said, and this was the proof that we did, right? Where x is equal to this, where did they start from? They use this, they basically solve for y. Yes, so you can go over this proof and you see that it makes a lot of sense, right? It makes so much sense why this is the Cramer's rule. Yeah. Let's see the next thing that we have to do. I think we are done with this slides. Now, the final thing that we'll be doing under matrix is the Gaussian elimination, the Gauss-Jordan elimination, and finally, plane transformation. We've done a lot today. We've done a lot of proofs, and the proofs are very boring. I'm sorry, but we have to go through them anyway, right? So this will be the final thing that we would be doing if there are no questions. But in the next session that we will be having, which is tomorrow at the same time, and we would be looking at the Gaussian elimination, the Gauss-Jordan elimination, and also plane transformation. Please, are there any questions? Is there something that is not clear in what I've explained so far? Any questions, please? Or you can please ask them here, because I think someone can benefit from your question. Any questions, please? Okay. So if there are no questions, I'll have a quick prayer. Then you call this a day. Father, we thank you for this opportunity. Grant us understanding as we study. Amen. So have a nice day, everyone. If you are in my 1 to 6 class and you are taking 1 to 2, okay, please let me know. Okay, so that I add you to the 1 to 2. Have a nice day, everyone. Bye.